Okay, so in this video, we look at another form of an attack known as microarchitectural attack, which essentially is able to bypass a lot of the operating system countermeasures or operating system security policies that are actually installed. Okay, so this class of attacks is known as microarchitectural attacks. It was discovered over 23 years ago, sometime around late 1990s, and but a lot of work came into prominence in 2018 and post 2018 when attacks such as the Meltdown and Spectre were essentially discovered. So let's start with the basics. So what we know is a computer system is arranged in a hierarchy. You have the processor and the rest of the hardware right at the bottom. Then you have the operating system, which is your system software and kind of acts as the resource manager and policy manager, which for your entire system. And then you have multiple different processes which are created by the operating system and use the hardware resources and share the hardware resources. Right, the operating system, as we've learned throughout the course, ensures that the various resources are mediated, are allocated and deallocated. CPUs are the CPU which is present in the hardware is scheduled and shared among these various processes, and so on. What the operating system also ensures, with the help of the hardware, that uh, that any OS data or information present within the operating system cannot flow from the OS to any of the user space applications, right? And the reason for this is because of the multiple privilege levels that are present. Now, in an x86 systems, we have 4 rings: ring 0, ring 1, ring 2, and ring 3. Ring 0 is where your operating system essentially executes from, while ring 3 typically is where your user processes like process 1, process 2, and process 3 execute one. So the ring 0 is the most privileged, while the ring 3 is the least privileged. Now, the least privileged processes are unable, so ring 3 for instance over here is unable is isolated and cannot read or access any data or information in ring 2, 1, and 0. Okay, so in general, any ring, say ring I, can only can access ring J such that J is greater than or equal to I, right? On the other hand, it cannot essentially access rings which are lower than that. That is, for instance, if I equal to 2, then ring 0 and ring 1 is not accessible, right? Another feature which we have studied in operating systems is the aspect of virtual memory. So each process that gets created runs in its own sandbox called the virtual memory address space, and we have this with the help of the operating system as well as the memory management unit. We create a hierarchy of page directory and page tables that would provide a contiguous address space for each process, and seamlessly these pages within the virtual address space is essentially mapped into the physical memory, that is the DRAM, right? And because of the sandbox created by the virtual address space, it is impossible for process 1, or for that matter any process, to essentially access data or any other information from another process, right? So these are the guarantees which an operating system essentially provides us. So it provides us that any process's data is sandboxed within its own process and cannot leak out directly to another process. Now, this is where microarchitectural attacks come into play. So, with the help of microarchitectural attacks, operating system data can essentially move from the more privileged rings to a lower or lesser privileged rings. In the same way, with the help of microarchitectural attacks, one process's data can be essentially leaked to another process data. in spite of having different virtual address spaces. Right. So, let us essentially see how these attacks work. Right. Now, fundamentally these attack works because of the shared hardware. Now, the presence of shared hardware, like for instance a shared cache memory in the processor, could lead to a channel through which information can leak from, say, a higher privileged software like the operating system to a lower privileged software like a user process. Right. So, here is an example of one such channel. Notice that the channel relies on the hardware to create or to transfer information from the OS in this example to the user process 1. In a similar way, the shared hardware resources could also be used to transfer information from process 2 to that of process 1, bypassing the sandboxed virtual address space of each process. Right. Again, the cost of this channel is due to the shared hardware resources like the cache memory or the branch predictor or the TLB that is present within the microprocessor. So, let us try to understand what causes these attacks. So, at a very high level, the entire processor state, right, can be divided into two parts. One is called the architectural state, which comprises of the registers and flags and other control status registers and so on, and this is typically visible to the software. So, the registers, for instance, in a RISC-V processor such as the R0 to R31 are your general purpose registers. Things like the program counter, the stack pointer, various control status registers like CSRs are all architectural registers because they are accessible through the software. Right. So, in general, any component of the processor, specifically any registers that are accessible through the software, is essentially called the architectural state. Now, the microarchitectural state of the processor, on the other hand, comprises of those regions of the processor which can store data but are inaccessible from the software. Right. So, cache memories is one example of this. While we can essentially store data in the cache memory, the cache sets or the cache lines are not directly addressable. And since they are not directly addressable, we call them as a part of the microarchitectural state. Now, there are a huge there is quite a bit, or there is a considerably large state that essentially falls into this type of category. So, besides the cache memory, you also have aspects such as the TLBs, you have the branch predictors, you have pipeline registers, you have FIFOs and queues that are essentially present with the processor. So, none of these are directly accessible from software, and therefore they are called the microarchitectural state. Right. So, here is an important distinguish. What is this? Okay. So, yeah. So when So, when an operating system, say for instance, switches from process 1 to process 2, what we have learned during this context switch is that the state of the process is essentially saved before it essentially switches to the next process. Right. Now, very importantly, and if we essentially go back to the classes on the context switch, what we see is that the state mostly comprises of the registers and other flag registers, the SATP register, and so on. So, all of this essentially forms the architectural state. So, in other words, when shifting from, or when context switching from one process to another, the operating system, because the OS is present in the software, is only able to access the architectural state comprising of these various registers. So, these registers are stored, and the corresponding context, the corresponding registers of process 2 is essentially loaded so as to enable process 2 to execute. The invisible state or the microarchitectural state is not affected when switching from process 1 to process 2. In other words, when we are context switching from process 1 or process 2, the microarchitectural state is not present. So, what this means is that even if process 2 continues to execute after the context switch, your microarchitectural state, for instance, in the cache memory or the branch prediction logic or any of the FIFOs or queues present very deep in the processor, would still have would still hold data of process 1. Okay. So, if process 2 is able to read out of this microarchitectural state, it may be able to gain some information about process 1. Now, if it is able to do so, what we are able to achieve is that we are able to obtain information about process 1 into process 2, right? Or in other words, we are able to bypass the sandbox environment created by the virtual address space so as to gain information about another process. So, how do we essentially, so the big question to be asked is, how do we essentially able to read the microarchitectural state? So in other words, we have the microarchitectural state and we want a particular process to read it out, right? We know that the microarchitectural state would have data of other processes that are executing, and we want to be able to read out that data to form this attack so that we are able to leak information about the other processes, right? There are several different forms of attacks that have been proposed over the last 20 to 25 years, and most of them make use of or are indirectly related to the execution time, right? We'll take an example of a very popular form of microarchitectural attack known as the cache timing attack. Now, before going into the details, we'll essentially look at what cache memories are. So, the typical organization of a processor is as follows. So, you have the processor, which is essentially fetching, decoding and executing instructions, and every time it wants to fetch instruction or wants to load or store data, it fetches that data from the main memory, that is your DRAM. Now, typically the processor is several times faster compared to the DRAM, which is made of which is composed of capacitors. Capacitors are good to store data in a highly dense manner, but it is not good to achieve the required performance. Now, to bridge the gap between the high speed processors and the slow dynamic RAM, modern systems introduce cache memories. So, cache memories essentially cache the recently used instructions and data. If a processor fetches a data from the DRAM, that data is essentially loaded into the processor, into a register present in the processor, but also is stored in the cache memory. Now, this particular load from the DRAM is going to take considerable amount of time because the DRAM is considerably slower than the processor. However, if there's a subsequent load to the same data, then since the data is present in the cache memory, the data can be directly read out of the cache memory into the processor. Now, this load is going to be considerably faster because the read or the load is from the cache memory and not the DRAM. So, the path taken when there is when the data is present in the cache is as follows, and it's typically called a cache hit. However, if the processor has to go all the way to the main memory or the DRAM to fetch the data, then it is a cache miss. So, typically we would have the cache hit or the time taken for the cache hit to be considerably lesser than the time taken for a cache miss. Okay. So, this is the basic premise by which microarchitectural attacks are built, and we would use this premise to be able to understand the microarchitectural state specifically the contents of the cache, and use this to essentially launch attacks. So we'll take an example of one such attack. So this is a cache timing attack used to break a cipher. So this is essentially a toy cipher, and we assume that there is a function involved called decrypt, receive decrypt. So this function takes a socket as an input parameter. There is a read system call that is invoked. The read is on the socket. It reads a ciphertext which is of one character. So CT is essentially the ciphertext. Now, to decrypt the ciphertext, there is a lookup which is essentially a global array of this particular form, and there is some data present over here. Now, the key, which is your secret key, XORed with the ciphertext which is received through the socket, is used to index into the lookup to get the corresponding plain text. Now, this plain text is essentially returned. So, notice two things, right? What we essentially want over here is to be able to predict the secret key, right? So, we want to be able to predict the secret key. Now, we are assuming that all of this is essentially running within a particular process. Now, the assumption here is that on the same machine at about the same time, we have an other process that is also executing, which is essentially sharing the same processor. Maybe it is running in parallel, or it is context switch with the same process, with this particular process. And the objective of this particular application is to be able to leak out the secret key from this receive decrypt. Okay, so how do we essentially do this? So first thing to observe is that there is a key dependent memory access for this particular lookup, right? So in other words, this lookup or the index to this lookup depends on the secret key in addition to the ciphertext. So notice that the ciphertext is essentially sent through the network. It may be received through a network through this particular socket. So it's quite likely that the ciphertext, which is in the encrypted form, is essentially known to the attacker. So in other words, what we have is the attacker knows the ciphertext CT, and we also assume due to some other mechanisms, the attacker also knows the address of the lookup. So for example, if the lookup array is present at say 0x1000, the attacker essentially knows the location of this particular lookup array. Now, given these two, and given the fact that the attacker can essentially run another process in the same computer at the same time as this particular process, which we call as a victim, we want to be able to extract the secret key 0x12. Okay. So, yeah, okay. So, this is the assumption that we essentially make, right? So, we have the victim, which we have essentially discussed, which is a process which is running, which has this function called receive decrypt. So, this receive decrypt is essentially in a process called the victim, and on the same computer system in a different CPU core, we have an attack process called the spy that is essentially executing. Now, what we essentially see over here is that even though the victim and the spy are executing on different CPU cores, they share the last level cache memory. Another way this attack can occur is when you have the victim and the spy essentially sharing a single CPU core. We have assumed here that this core is symmetrically multi-threaded, or an SMT core, right? So we have the victim and the spy sharing the same cache memory, right? Now, internally, we are going to consider this particular scenario where we have one core, we have the L1 cache memory shared between the victim and the spy process. So a typical L1 cache memory looks like this. We have cache lines which are present, and these cache lines are organized in sets. So here, for instance, we have n sets labeled set 0 to set n minus 1, and each set has holds 4 cache lines. So this would be a 4-way set associative cache. So we have way 0, way 1, way 2, and way 3. Now let us say that the attacker runs a particular program in the spy. So this is my spy process, and within the spy process, the attacker essentially runs this particular while loop. So notice it's an infinite while loop, right? What it does is that it, within each iteration of the while loop, it has this inner for loop, which essentially accesses each cache line in a particular set. So for instance, in the first iteration, the cache line is in set zeros are accessed. So how is this made possible? So this is made possible by essentially loading data from specific addresses so that those addresses are mapped to set 0. So also during each iteration, the spy measures the time taken to access the cacheways, right? So the access time for a particular set is given by end minus start, where end is the time when the or n minus start, full stop, okay? And yeah, and this is done continuously for each cache set. So notice this first thing, right? So yeah, so during the first iteration of this while loop, this cache has no information or does not contain any data about the spy. Therefore, each iteration of the for loop would result in a large amount of cache misses. So 4 cache misses in each case, right? And thus, the first iteration of the while loop, there will be a large number of cache misses. Now, as we know that the cache miss is considerably slower than a cache miss, and therefore the time taken to load data, or the access time for each cache set, would be considerably large. So this phase is essentially called the prime phase. Now for subsequent iterations, the iterations after the first iteration in the while loop, the access time for each cache set would be considerably lesser, because the data for the spy is already present in the cache, right? So any load or any access to these data is directly read from the cache and does not need to go all the way to the main memory. Now let us assume that after some time the victim executes, and the victim essentially performs certain accesses which are very specific to its execution pattern. So for instance, the in the victim that we have actually assumed, we see that the victim would essentially perform an operation such as the victim would so in the example victim that we have seen, we see that there is a statement such as this: pt equal to lookup key XOR with ct, right? So when the victim executes, we are assuming that this particular access is essentially performed. Now what we see is that based on these values of key and ciphertext, this lookup would be essentially performed. So for instance, if the key happens to be 0, and let's say the ciphertext also happens to be 0, then the net result would be lookup at index 0, which would cause a very specific cache set to be accessed. On the other hand, if we have a value, let us say key is say 80 and ciphertext is say 1, right? So this would essentially lead to an index in the lookup which would cause a different cache set to be accessed, right? So in other words, what we can say is that execution of this particular statement, where a specific byte within lookup array is accessed, would indirectly affect the cache state, right? So depending on what index is accessed, you may have a specific cache set that gets accessed, right? And since the cache is essentially shared between multiple processes within the sharing the CPU, such an access would evict the spy's data and replace it with the victim's data. So as we see over here, we have the spy data, which is blue, sometimes getting evicted out and replaced by the victim data, say in set 1, set 2, set 3, but not in set 0 and set n minus 1, right? So now we have the third phase, which is the probe phase of this attack, where the attacker, which is the spy process, continues to execute this particular while loop. And now, as before, it starts to access each cache set and also identify the access time or the time taken for each cache set. Okay, so based on the time, it could actually infer something, right? So, for instance, the time taken, what it would actually observe is that the time taken to access set 0 would be lesser compared the time to the time taken to access set 1. The reason for this is that set 0 4 cache hits, and cache hits can be completed considerably quickly. On the other hand, when this spy process during the second iteration of the for loop is accessing, say, set 1, it would observe 3 cache hits, which would be considerably quicker, and 1 cache miss, where the data of the spy has been evicted and replaced with the victim's data, right? Now, to service this particular cache miss, the spy, the processor, would need to go to a lower memory, for example the DRAM, and pick the data to which is then stored in the cache. So this would essentially take considerably more time than having a cache hit. So at the end of this for loop, the attacker, that is the spy process, would be able to distinguish between cache sets which had a lower access time compared to cache sets which had a higher access time, right? And from this information, it would be able to identify which of the cache sets have been touched or modified by the victim process. So given this particular information, it can then use that to get a notion of what index in the lookup had been essentially accessed. Now, given that the attacker knows the ciphertext, if it also knows information about the index that has been accessed, it can essentially use this relationship to identify certain bits of the secret key, right? So what we see this way is that certain bits of the secret key present in the victim process can be leaked through the cache memory to an other process called the spy process, which is controlled by an attacker, right? So here is an example of the probe time plot. This is essentially taken on an Intel 5 platform. So what we see over here is it's 0 to 63. So we see each column here corresponds to a cache set. This is an Intel platform, and the L1 cache has 64 cache sets, right? And therefore each column corresponds to one particular cache set. So you have 0 to 63, and the y-axis you see these numbers 480, 490, and so on. These are essentially the iterations of the while loop. So for example, the 480th iteration of the while loop corresponds to this row, 490th is this row, and so on. So what we see is different shades of gray, and the darker shades imply a higher access time, right? So for instance, you would see that certain columns or certain cache sets, like for example this, has considerably higher access time compared to, say, this particular cache set. So what this essentially means is that there is more likely chance of a cache miss occurring in this particular cache set compared to this this cache set, right? So what we are observing from this is that we can now distinguish, with the help of the spy process, what cache sets were accessed by the victim during its execution. Now, using relationships, using the structure of the program of the victim, we can then infer secret information. For example, in the example that we have taken, we can possibly infer certain bits of the secret key. Okay. So, another region which is also interesting is this region. So, roughly from 630 to 660 iterations of the while loop, we see that there is a patch of gray, of darker color, which essentially means that during this process, during this time, there was significant activity in the processor, maybe due to um, maybe a context switch or an interrupt or something, which essentially caused a lot of disturbance in the cache, and the spy has recorded this disturbance with an increase in the access time. So what we see with this particular probe time plot is that we can kind of monitor the cache memory behavior in terms of number of in terms of hits and misses, and from this behavior we can then try to speculate or try to infer what has essentially caused or what has essentially happened with other processes executing on and sharing the same cache memory, right? So we showed an example of how uh, something like a secret cryptographic key can be essentially leaked through the cache memory. Such prime and probe attacks are also used for other applications. For example, it has been used to sniff keystrokes. For example, you have, let's say, a victim application where you have a user who is entering or typing an email or entering the password or a credit card number, and you have a process P2, which is your spy process, which is essentially sniffing or monitoring the cache behavior through its access patterns, right? Now, as the process P1, the victim process, is executing, and as the user is essentially typing through the keyboard, each keystroke would result in an interrupt. Each interrupt causes a switch to the kernel mode, as we've seen before, and causes the execution of an interrupt service routine, or the ISR. And this ISR essentially identifies what key has been pressed and then reads that key from the keyboard buffer. All of this process, interrupt, switch to kernel mode, saving the context, executing the interrupt service routine, reading from the keyboard, and so on, has significant amount of operations, and therefore this would essentially affect considerably the state of the cache memory, right? So from a spy process which is continuously monitoring the cache for its access time for each set, the spy would essentially observe certain spikes in the behavior. So for example, every time there is a spike over a period of time, it would essentially mean that the access time had been longer at that particular instant. So for instance, here, here and here, for instance, is where we have observed a higher access time, and this could possibly be due to a user essentially pressing or typing in a keyboard, right? So using this access time pattern, right, the attacker would be able to model a particular behavior and then reverse engineer reverse engineer to identify what keys have been pressed. So for example, over here, using this graph, using this series, this time series as input, the attacker would be able to reverse engineer and identify that the keys pressed was admin 1, 2, 3, and then an enter. So such kind of microarchitectural attacks, the prime and probe attack in particular, have been used for cryptographic for stealing cryptographic keys, for website for what is this, for keystroke sniffing to identify what keys have been pressed in another application. It has also been used in web browser attacks, right? Especially if your browser uses JavaScript or native or the native client or WebAssembly. The attacks can be used, or your spy process can essentially execute, for example, as a WebAssembly or as a native client, and this could essentially lead to remote attacks. So, for instance, um, here is an example from Iran Trauma's paper, Drive by Cache, where there are 3 tabs which are open on this particular browser. The first tab is where there is an encrypted email that is essentially present, while the second and third tab are possibly a malicious tab. Now, these second and third tabs would possibly execute a spy process, maybe written in JavaScript or in WebAssembly, and which essentially at a high level performs exactly the same thing of performing some memory accesses and monitoring the amount of time taken to perform these memory accesses. Now, through the time, it's able to profile the cache memory usage based on how long or how short the time was taken for each cache set. Now, using this, the attack in this particular paper showed how an encrypted email can be essentially decrypted uh, using the cache profile observed by the spy process.